Hi everybody, my name is Rachel Kowski and our lab is titled Static and Kinetic Friction of Different Surfaces. This is our modified version of Lab 5, which was titled Coefficient of Frictions. So we're trying to prove a couple of different objectives with this lab. One goal that we're trying to prove is that you can find static and kinetic friction using different methods. Another goal we're trying to prove is that using different surfaces, two different surfaces will also produce different static and kinetic frictions.
Hello everybody, my name is Dylan, and the theory behind our lab is that there are two different friction forces that we are finding here. We are finding static friction and kinetic friction. Kinetic friction is when there's an object in motion and it's in contact with another object. An example of this would be a car driving down the road and then slamming on the brakes. And then static friction is when there are two objects in contact, but they aren't moving. They are in one place. An example of this would be like a car parked up on a hill. So there are two formulas that we use in this experiment. The first one being for static force, which is just mass times gravity times the cosine of the angle theta. And the way that we cancel out cosine angle theta is we made a pulley system on a flat surface where the piece of wood was. So that way the angle would just cancel out. So this isn't even part of the equation anymore. So it's just mass times gravity, which is much easier to find. And then kinetic friction, the only time we can use this formula is if the acceleration is 0. We'll come back to that later. But the formula is the coefficient of kinetic friction multiplied by mass multiplied by gravity multiplied by the cosine of angle theta, which is equal to mass times gravity times sine angle theta. So since mass times gravity is on both sides, we can cancel those out. And then we just divide sine by cosine over here, which turns it into tangent. And so it simplifies into just the coefficient of kinetic friction is equal to tangent of the angle theta.
So on the table are all the materials that we used for our project. And here we have the two surfaces that we use. So this is the plank of wood and piece of cardboard. This is the block of wood we use to slide down these materials, and as you can see there's a rubber pad here, just another difference from Lab 5, just to separate the contact between these two. And here's a flag that we constructed for when it is passing through the photo gate over here, so that it actually detects it as it goes through. We use 2 meter sticks for measuring. Here are some weights and a hook to put the weights on, as well as a pulley with some string, and our Pasco system.
So the first thing that we found was the static force. We did that by putting down the wooden plank here and then attaching a pulley on this end of it. So the formula is mass times gravity times the cosine of the angle theta. So by putting this pulley here on the same level as the object, we'll cancel that out. So it's just mass times gravity. And so we need to find the minimum amount of mass it takes to get this block to get to motion from standing still. And so you do that by slowly adding these little weights until you find a weight that will make it move. And since it's kind of a rubbery substance on the bottom, you kind of have to give it a little bit of a push. But if you just give it a little tap and start to slowly move like that, that's the weight that you want. Like that. And then we repeated the same process with the cardboard as well. All right, so to set up the Pasco photo gate, the first thing you want to do is go up to the hardware setup, click the place where you plug it in, select photo gate, and then you set it up over here. So you want to do the pre-configured timer here, select photo gate. You want to select the single flag here since we only have one. You don't need time and gate or state, you just need speed. And then you need to measure the length of the flag and then enter it in here. And then you hit finish and then you are all set up. You can just bring a table on over here and select speed as your measurement, and you'll find the speed of your object in this column right here.
In order to begin the procedure for kinetic friction, you want to have your wooden plank and your meter stick right up against the surface here. and you're bored with the flag. The goal is to get the plank to pass through the gate as cleanly as possible. You want to have a constant velocity so that acceleration is 0, so that the formula will work for this. And you're going to pick 5 different adjacent measurements here. So like 80, 70, 60, whatever you want, 5 different ones, and you're going to do 10 trials for all of them. You begin by lifting the plank up until the board begins to move and you have a constant velocity. So it's important to keep the board at the same angle so that you can measure at the opposite height. So if our adjacent measurement was 70, you can place the other meter stick right there to get a precise measurement. So remember to do 10 trials of that adjacent length that you chose, and then choose 4 more adjacent measurements. After you've completed the experiment using the wooden plank, repeat the procedure with the cardboard.
For the results of our project, this first tab here is for static force. So as you can see, the wood had a static force of 0.73. We found that by moving at the weight of 0.075 kilograms, then we multiplied that by the force of gravity, which gives us static force. And then cardboard, it only took 0.1 kilograms to get the piece of wood to move. So the static force was much lower at 0.098. And these were the results for the kinetic friction part of the experiment. So this first part here was for the wooden plank, and as you can see, the 5 different adjacent length values that we took, the 90.5, the 70, the 50, 30, and 10, and then the matching opposite lengths that we took for each of our trials. And then what we did is we took the average of the opposite lengths for those 5 different measurements and then put it in a table and then made a graph off of that table. And then we put adjacent on the y-axis and the opposite length on the x-axis. And then we put in a trend line and got the equation, which gives us the slope right here. And this slope is equal to the tangent that we saw in the earlier formula. And the tangent is equal to the kinetic friction value. And so our value for the wood was 2.03, and we had an r-squared value of 0.997, which is very close to 1, which is what you want to see. And then what we also did is took the standard deviation of the speed, so that way we can check how close we were to keeping the same speed. And as you can see, these are all really low values, which is good. And then for the cardboard, we did the same thing. We took the 5 values and then averaged the opposite values that we got, put it in a table, and then made another graph with adjacent on the y, opposite on the x, and then got the kinetic friction value of 1.69 and an r-squared value of 0.999. So our conclusion is that cardboard does not generate as much friction as wood, since it has a much smaller static force. And we see that again with the kinetic friction values too, with the kinetic friction value for wood being just over 2 and this value being at 1.7. So cardboard again had a lower kinetic friction value. So one thing we would change in future labs would be a better way to measure the opposite length. The way we did it is just by raising up until there was a constant velocity. But even then, there's a little bit of arm movement that's uncontrollable. And so when we measured, there was a little bit of variation. So if we could find a way to keep it steady, that would vastly improve the precision of the experiment.